Okay, within the proof of that angle formula, we came up with an alternative form of the dot product. I don't know if you remember, it was at the end of class last time, so you were probably getting sleepy. I know I was. But it turns out that the dot product between two vectors, u and v, well, I mean, just think about the cosine formula for theta in terms of u and v, and multiply both sides by the magnitude of u times the magnitude of v, that denominator, and you get an alternative form. The u dot v is equal to magnitude u times magnitude v times the cosine of theta. And in physics class, you might actually define the dot product this way and then derive the formula that we came up with. So why is it useful to think of the dot product in terms of magnitude u times magnitude v times the cosine of theta? Well, you get some interesting things. We talked about note number 1 last time, and by the way, the assumption is that u and v don't have components that are all 0. It could have some components 0, but not all of them. Otherwise, if u is the 0 vector and you dot it with any vector, you get 0, right? So the assumption is that they're not equal, neither one, u nor v, are equal to the 0 vector. So when is u dot v equal to 0? Well, if we know that u and v are not the 0 vector, these magnitudes are always going to be bigger than 0, right? It's always bigger than 0 if the components are non-zero, not all 0. So it's really the angle that determines when we get a dot product of 0 in that case, isn't it? Well, for what angle is the cosine of theta equal to 0? 90 degrees. So this IFF means if and only if. So u dot v is equal to 0 if and only if theta equals pi over 2 in radians or 90 degrees. Right? So the dot product is an orthogonal vector detector. I just like saying that. I think it rolls off the tongue. But wait, there's more, and this becomes important much later in the class. We actually know when, and I kind of gave this away already, we actually know when u dot v is bigger than 0 from this alternative formula. So think quadrant-wise. You know what I mean by quadrant 1, quadrant 2 in the xy plane, or in any plane, really. For which quadrant is the cosine positive? Well, the one where, there's 2 of them, but the one we're interested in. Quadrant 1, also quadrant 4, but we're not going to talk about that as an angle between 2 vectors. So in quadrant 1, we know that the cosine's positive. In quadrant 1, the cosine's bigger than 0, isn't it? So we know then for note number 2, if u dot v is greater than 0, if and only if theta is in quadrant 1, if and only if theta is between, well, we'll talk about the endpoints in a minute, but between 0 and, well, 90 degrees if you like degrees, or radians if you like. It really doesn't matter. So what about the endpoints? What about when theta is actually equal to 0 degrees or 0 radians? What's the value of the cosine of 0? 1. Oh, so that means the dot product would be positive in that case. But as we've already demonstrated, we can't include the 90 degrees, right? Because we actually get a value of 0 for the dot product when theta is equal to 90 degrees. Okay, so what is that telling us? That's telling us if the 2 vectors are pointing kind of in the same direction. In other words, so pretend like that's u and that's v. If this angle's acute, does that mean an adorable little angle? Sure. No, if theta is between 0 and 90 degrees, if theta is acute, then the dot product is positive. So going the other way, if the dot product is positive, then we know that the vectors kind of point in the same direction. Not exactly, well, I suppose if the angle between them is 0, they point exactly in the same direction, right? But if theta is acute, then they point more or less in the same direction, and we can tell that symbolically by just computing the dot product. So the vectors point in similar direction, we'll say. Whereas if you, note number 3, if u dot v is less than 0, well, what do you think that says about the angle, first of all? Which quadrant would it have to be in? You only have 2 choices, 1 or 2. It's got to be in quadrant 2 between 90 and 180. So theta is between, if we're talking degrees, 90 degrees and 180 degrees. Oh, wait. Let me not include the 90. Are we going to include the 180? Yeah, because what's the cosine of 180 degrees? -1. So we can't include, and so that would make the whole thing negative. So what does that mean? That means that the angle between the vectors is, what's the word we use? Obtuse. Or the vectors point kind of in opposite directions, not totally opposite unless theta is 180, but kind of in opposite directions. U and V point in opposite directions. I'll use a wavy equal sign, approximately opposite directions, when u dot v is less than 0. And whenever you see the if and only if statement, it means the statement works in both ways. So if you read it from left to right as an if-then statement, you can say if u dot v is less than 0, then theta is obtuse. Or read it the other way. If theta is obtuse, then the dot product between u and v is 0. It works, that if and only if means you can read the statement in both directions. Does that make sense? Yes?
What about third and fourth quadrants?
Recall that when we're talking the angle between 2 vectors, we're talking about the smaller angle. Okay, it's always going to be between, any way you draw it, the only way you can draw it is that it's between 0 and 180. It's either acute, an adorable little angle, acute, right? That's what acute means, or it's obtuse. So just to emphasize then, u and v are orthogonal. Have we talked about the word orthogonal? U and v are orthogonal, which means, well, I have it written here, perpendicular. If and only if, well, it's already written in statement number 1, right? If and only if u dot v is equal to 0. So I'm kind of repeating myself there, but it's important to use the terminology orthogonal. So the dot product is an orthogonal vector detector. Okay, remember that. That's an easy way to determine whether or not 2 vectors are perpendicular to each other. So if you want to check to see if u and v are orthogonal, just take the dot product, see if you get 0.